Hello and welcome here at Rust Linz. We are glad to have you. It is a beautiful summer evening, and so I thought I'd just move in the garden today. So today I'm broadcasting here from Leonding near Linz, and I'm super happy that you are all our guests today. We are looking forward to two super interesting sessions about two interesting topics around Rust, and I will kick off the evening with a round of community news. Let me share my screen with you. And here is my screen, and I will go into presentation mode. It's a kind of a nice tradition for all the Rust Linz evenings that we spend today, that we start the evening with some news about what's going on in the IT community in Linz and about Rust in general. So this is what we are going to spend a few minutes on. So this is already the 33rd Rust Linz Meetup, and we are super happy that we always find so many interesting speakers who agree to spend their time here together with us, sometimes virtually like today and sometimes in person in Linz. So let's get started. As you all know, the Rust Linz Meetup is brought to you by the Coding Club Linz. The Coding Club Linz is a community of professional software developers who are passionate about coding and passionate about teaching coding. Today's speakers, we have two speakers today. Shachar will kick off the evening with his talk, Async and FFI, not exactly a love story. We are very much looking forward to this talk. He is our first guest speaker of the evening. The second speaker is our very own Stefan Baumgartner. Stefan will talk about trials, traits, and tribulations. We are looking forward to have another talk of Stefan here at Rust Linz. So right after the community news, we will start with Shachar. If you would like to join our community, you can always do that by joining our Discord server. Here you see the link to the Discord server. Feel free to join. You can use the Discord server to get in contact with us. You can use the Discord server to ask questions during our Rust Linz meetups. So these are the main use cases for our Discord server. Here is the link, and after the quick introduction, I will also post this link in the YouTube chat, so you can just click on this link and hopefully everything will be fine. Now, community news. The first community news comes from our own community, Coder Dojo Linz. Coder Dojo is a programming club for kids that we have been running for over 8 years now, and in the last weeks they were pretty busy for us. We had the Ars Electronica Festival, which is a huge digital arts festival here in Linz. People from all over the world are coming to this festival, and we had our own booth where we had, I think, over 1,000 people over the course of 5 days visiting our booth, doing some interesting experiments with us. We had an artificial intelligence stuff, and we had a lot of kids doing soldering, tinkering, and coding with us. So it was awesome here at the Ars Electronica, and if you ever want to visit Linz, definitely try to come to the Ars Electronica Festival. It's definitely worthwhile. Now this brings us to the events. Coder Dojo Linz happens tomorrow. As every Friday, we will have a programming club for kids for free. Friday afternoon, you can check out the topics here at this URL. Next week, we will have another meetup. This is a rather young meetup in our coding club Linz. It's a Teach to Code meetup. It's a meetup where we invite people who teach electronic and coding to other people, to especially kids and young coders. And this meetup is going to happen next week on Tuesday is the next edition. And I will also post this link in the YouTube chat. So if you are interested, just click on it and we would be happy to visit to see you there. The next thing that we would like to point your attention to are female coders. Female coders, our friends at Female Coders, they run an awesome community in Linz. They do regular study groups for women and girls who either are in IT or who would like to get into IT, and their next study group will be on the 4th of October. As before, I will post the link to the Female Coders website afterwards in the YouTube chat. A very vibrant community here in Linz is the Cloud Native community, and they have their next meetup on the 18th of October. And the core topic, one of the most important topics I personally think that it's super interesting is open telemetry. We are looking forward to seeing this meetup happening on the 18th of October. If you are interested in Cloud Native, definitely check out their website. Link is here in the slides. Now, Eurorust is also around the corner. It will happen on October 12th and 13th. It's very special for us here at Rust Linz because Stefan will give talks and I think also a workshop there. I put the announcement here in the community news, but a few minutes before today's meetup, Stefan told me that Eurorust is already sold out. So if you haven't got a ticket yet, I'm very sorry. It is sold out for this year, but there's always a next year. So hopefully we will see many of you at the Eurorust in October in Brussels or online. Now, one of the largest meetups that we have here in Linz is the Technologieplauschel. Stefan is a co-initiator of this meetup, and therefore it's very important for us. The Technologieplauschel is a great possibility to meet like-minded people, to talk about various topics, not just about Rust, but general IT topics. But Technologieplauschel is always open for speakers who would like to talk about Rust. So if you would like to join one of the next Technologieplauschels, just fill out their call for speakers and they are glad to have you. The next Technologieplauschel will be on the 18th of October. And last but not least, Stefan asked me to point out another community, the Rust Lab conference in Florence, where he will also do a talk. And I think with that, yes, we are through. That's it. That was the community news. And I think I finished in time. Yes, it's 5:37. That sounds good. And let me stop my screen sharing and ask Shachar to come to me on the stage. Hi, Shachar.
Hello.
Hi, how are you?
I'm fine. It's a lovely evening here too in Israel.
Very nice. We have a lot of sun here. I'm sitting under blue sky, a beautiful autumn evening. So best time to talk about Rust and have some interesting talks about it. Hey, Shashar, you said you have a nice evening here in Israel. You broadcasting from Israel? Did I get that correctly?
Yes, I'm in Jerusalem.
Very nice. So, greetings to Jerusalem. We are really an international crowd here. Jerusalem visiting Linz. I love that. Shashar, you are going to talk about async and FFI, right?
Yes, exactly.
Awesome. So, Shashar, we are very much looking forward to your talk. I am handing the stage over to you, and I will be here if you need anything. If anything goes wrong, maybe some technical issues, just tell me, and I will be back with you on stage. Enjoy your talk here at Rust Linz. We are very, very glad that you take the time and that you are with us today.
Thank you very much. So, just to introduce myself for a bit, my name is Shaha. I work at AWS, and the talk I'm going to give today is shares some of my experience for the last year or so. Uh, you can see the sample image I have. I generated it using, I forget which AI, and I think it represents well what I'm going to talk about because you can see what I tried to do there, but it doesn't really work out. And I think that the experience of trying to make FFI and async workloads work together well feels a bit like this. It works. It's not exactly what he wanted to do. So, what am I going to talk about today? Um, I am going to talk about, a moment, yes. I'm going to talk today about an application. Let's say it's written in another language, higher language, garbage collected language. In this example, it's a Java application. And in that application, we want to call into some asynchronous Rust code. In my example, we have some database client, and that database client calls to the database over a network. It performs some kind of asynchronous operation, that is, an operation where you send data and wait for it to return. And we want to send a request from the Java layer of the application to Rust. We want the Rust layer to send a request over the network and get the response, and then pass that response back to Java. Now, this so far is pretty simple. It's being done with FFI daily, but we have a, a slightly added requirement. We want that after we send our request on the network, that the Rust thread, the Rust logic, would be able to sort of just sit idle and wait for the response to go and do other work. And by the same token, we want also the Java logic to not be blocked either by the Rust code or by the network code, and to go and do something else so that the Rust code will not be blocked by the network, the Java code will not be blocked by the Rust code, and essentially this is what we're talking about when we say asynchronous programming, that we run things that allow us to run in a way which is not synchronized, that we're not blocked and waiting until the last thing ends. Now, these days, asynchronous coding is very easy compared to where it was 10 or 20 years ago. Most languages have some kind of, maybe most languages is an exaggeration, but a lot of common languages have async and await syntax that allows us to write a function that mostly looks like a regular function, but in the middle, it uses the await keyword to say, this is a point in which this function will hang, will stop, or will yield control, and something else can run in the meanwhile. And the next line will wait until some condition is met, some kind of external trigger is triggered, and then the next line will run. But the next line behaves just like the next line in a regular function. So we have the async keyword saying in this function we might yield control, and we have the await keyword saying in this line we actually yield control. And this makes life very easy because this function does something very complex. You might see the function saying send something on a network and do something else with a response that you get. But there's also a whole invisible mechanism saying send something on a network, check if there's other work to do while we wait for the response on the network, perform the other work, receive the response from the network, stop doing the other work, handle the response on the network, and continue to do something. And it's easy to write. It helps us reason about concurrency, about things like I/O, network activity, etc. Asynchronous programming is easier today. Another thing which is easier today is using code written in one language and consuming it in another language. Right? We want the ability to, it's fairly common today to be able to call from one language into another language within the same process. But why would you do something like that? Often you do it for better performance. Now, better performance might be faster code, or it might be code which uses less memory, less computer resources. You write some code in a language where you have a lot of control over your resource usage, such as Rust, C, or C++, and you write your more complex code where you're not performance oriented in a language which might be simpler, such as JavaScript or Python. You might just have a lot of languages that you work in, and you have some complex functionality that you want to write once and then consume it in a lot of languages instead of implementing that complex functionality in a lot of languages and having the potential of differing behaviors of each implementation varying slightly from the others. Or you just might have existing code written in one language, and you have the rest of your code base or your new project is written in another language, and you don't want to rewrite whatever you have. And you don't want to rewrite your existing code. You just want to call into it. So there's a lot of reasons to use calls between languages, and we call this FFI, Foreign Function Interface. Foreign as in something different, something which is not native to your language. Functions are functions. I'm sorry, my phone seems to refuse to shut itself, so excuse me. Functions are functions, and interface saying essentially this is how it will look. This is the promises we give you. I gave a talk, it's available on YouTube, at length about the concepts and problems in the general case of foreign function interfaces. You can watch it later. Today's talk doesn't assume a lot of knowledge. I'll try to cover the basics in the beginning, but here we're going to talk specifically about the issues with asynchronous programming. Now, one concept that we do need to understand before we go into asynchronous programming is the concept of ABI. We know the term API. API, an application programming interface, is the interface that is exposed to the programmer by a library, by a language, and essentially gives the programmer promises about that interface. It defines things like what functions you have, which arguments the functions take, what's the return types of functions, what the functions actually do, etc. It gives to the programmer promises about the library. And an ABI does something similar, only instead of giving promises to a programmer, it gives these promises to other programs, to other languages, or between libraries too. It defines things such as which CPU registers you use for input or output, what is the size and alignment of structs, etc. And essentially, both these interfaces provide the same idea. They give us the promise that as long as an API or ABI does not change, even if the implementation, the library version has changed, externally you can still use the library, you can still use the code and get the same effect. So an ABI is an interface. It is the equivalent of an API between languages. And how do we define this interface? Well, commonly today, we use C as the de facto API to be used between languages. So what do we get when we say we use C? It means that when we call between languages, we can pass primitives back and forth, right? Integers, floating points, as long as they're defined in C, we can safely pass them. We can pass raw pointers between languages. I'm not talking here about Rust references, but actual pointers to areas in memory, and functions. But again, not functions such as C# functions or Rust functions, but the equivalent C function. Now, C also allows us to use structs, but in reality, we almost never actually use structs in FFI, simply because higher languages usually have reference semantics and they don't have value semantics, and it's a bit hard to create a struct in a language like Java, JavaScript, or Python. So usually it means that when we talk between languages, we need to be able to talk in primitives, pointers, and free C functions. And the next concept we should understand is marshalling. Marshalling is essentially the conversion of data from one form to another. So if we have a string in C# and we want to pass it to Rust, we need to marshal the C# string into a Rust string. That means that we might need to re-encode it. If it's a garbage collected string, we need to tell the garbage collector not to manage it while it's being handled by Rust. If it's a buffer or a number, we need to make sure that its endianness is correct, because some languages use endianness based on the machine and some have a set endianness. If we're passing functions, we make sure that if I say in C# or in JavaScript, call this function once a computation completes, we give a C# or JavaScript function, we need to convert it into a C function, which is callable from another language. And as I mentioned, we need to make sure that every value we pass, if it's tracked by a garbage collector, isn't garbage collected while we're using it. So these are the basic concepts. We have an ABI, which is essentially what C gives us in order to talk between languages, and anything we pass between languages has to be converted to to a format which is usable by the other language. So Now that we put the basic groundwork, let's talk about asynchronous programming. So the first thing to know about asynchronous programming is it's not so simple. You'll see frameworks, you'll see binding libraries which allow you to create functions, asynchronous functions between languages, but the reality behind it is rather complex, and this complexity and the inherent problems are going to be the crux of what I'm going to talk about. I'll cover in very rough lines 3 main issues. First of all, the practical issues. How do we manage threads? How do we manage CPU time between languages? Then I'll explain in a higher level, why do we have these problems? What's the conceptual problem that means that even though we have structures that are meant, as I started, to give us an easy asynchronous programming experience, why they complicate the experience. And then I'll finish with the less basic problem of why performance isn't that great when you use FFI and where's the costs. So without further ado, let's go into the practical problem. So we said we have a Java application calling into some Rust library. And here we'll go down a level and talk about threads, about the actual units of execution running the code. So we have a Java thread, and the Java thread wants to call into an asynchronous Rust computation. It knows that it's going to perform an asynchronous computation. So the first thing it does is creates a future, something that will encompass the computation and will inform the Java framework when the computation is complete, so that it can go on, in our example, to the next line afterwards. After it has created a future, it takes the arguments it wants to pass to Rust and marshals them to a shape which is consumable by Rust. It takes the callback it wants Rust to call once the computation completes and marshals it into the shape usable by Rust. Rust receives these arguments, receives the callback, performs some asynchronous computation, sends its data over the network back to the database, receives the response, and in the meanwhile, the Java thread is free to do something else. It doesn't need to wait. The Rust side has received the response. It has a callback. It calls the callback back into Java land. The future is resolved with the response from the database. The Java code can go back and continue its work, and the Rust thread is free to go back and perform the next task or whatever else it needs to do at the same time. This is the experience we want. But if we do some things incorrectly, if we make mistakes, then there are a couple of pitfalls we should be aware of. The first one is thread exhaustion. If we do everything correctly, Java threads do Java work, Rust threads do Rust work, and as long as each one of the frameworks has enough threads, everything works okay. But if we make a mistake, then suddenly we said resolve the future, the Java future, using the Rust thread. The Rust thread resolves the future, and once the future is resolved, it executes the next command. What executes the next command? The thread which resolved the future. Now, this is because there is nothing inherently different about Rust threads or Java threads. Both of them are operating system threads, and they can they can be used interchangeably. If we don't remember at the point where we're resolving the future, or if our framework doesn't force us to do that, and if we don't remember to resolve the future and continue with the correct thread, with a Java thread, then we might start moving our Rust threads to perform Java work. And if we do that, then eventually all of our threads, both the threads we allocated for Java and the threads we allocated for Rust, will be busy doing Rust work. And until some thread will come and create a new future and stop doing, until there will be nothing left to do on the Java side, and threads will be released and maybe go back to performing Rust things, the Rust side of the computation will be completely starved. We won't have threads to send requests on the network. We won't have threads to parse the responses, and we won't have threads to call the callbacks, and our program will hang. Another problem that we might have is that we skipped the context switch. That is, in our Java thread called into Rust, but was not released. It is somehow, for some reason, still hanging on on waiting for Rust work, and it is blocked there. And again, this might cause us to exhaust the Java threads because they will all be blocked. Or worse, we might not switch work from Java threads to Rust threads, and suddenly all of our work will be performed on Java using Java threads. And we've halved our available thread pool, and we have some threads doing nothing and other threads doing twice the work. Now, why would this happen? Why would threads do twice the work, and what manages which thread does what? Why do we even need the separation? In order to understand that, we need to understand what allows us to make async programming. And these structures are called, in Rust, they're called runtimes. Each language has its own name for it. So how do we do async computation? What are the basic building blocks that programmers in different languages expect to have? In JavaScript, they're called promises. In C#, they're called tasks. In Python, they're called futures. In Rust, they're also called futures. In C++, they're called futures or coroutines or senders and receivers. But in C, we don't have any such concept. We only have void pointer, a pointer to something. So again, if we remember that, and sorry, well, I'll get into the ramification of that later. But what runs these promises, tasks, and future? In JavaScript, it's called the event loop. In C#, it's the task programming library. Executors in Python, runtimes in Rust. I'm really not sure what happens in C++. And again, nothing which is language oriented in C. So what do these runtimes do? They have a pool of ready tasks, tasks which should be executed. And they have another list of tasks which are currently waiting for some kind of external trigger, a response on the network, files to be retrieved from a disk, something like that. The runtime takes a task from the ready list, runs it, executes the commands that the CPU needs to do until it reaches a point where it's waiting for an external trigger. It sent the response on the network, it went to the hard disk and requested that file, and now it puts the task in the waiting list, and schedules it to run once the response is received. But after scheduling it, after putting it in the list of waiting tasks, we can go back to the list of ready tasks and get a new task to run. This is our ability to perform things concurrently. The fact that one task is waiting for something that is not within the CPU's control doesn't mean that we should just stop. We can go and find another task which is within the CPU's control and execute it. So in other words, runtimes schedule CPU time between concurrent tasks. They allow each task to run, and once the task doesn't have anything more to do with the CPU, it waits for it. It puts it aside until it will wake up. And when whatever it's waiting for will happen, in the meanwhile, don't block the CPU. Use the CPU to do something else. Now, our problem is that runtimes look only at themselves. There is that each runtime assumes it has control of all of the threads. It views all of the tasks. It doesn't know how to talk to other runtimes. And I'll remind you that when we talk about runtimes running between languages, there is no interface which is runtime aware to talk with. If runtimes talk between languages only in C, C offers us no ABI, no concept of asynchronous operations. So there is nothing that allows a Java executor to be aware of the Rust Tokyo runtime. There is no language to communicate the fact that the Tokyo runtime has a task which is waiting for the network. So the reason that we need this slide and have this thread using that resource and calling that thread is because of this. Because there is no higher level ABI for the two runtimes to communicate between each other. A runtime which manages one set of threads can only talk in basic thread speak of whatever the operation provides it with another runtime. It doesn't have a higher level interface to say, I'm awaiting you. This is my promise. Take it as an asynchronous task in your level and complete it. It has to be reduced to whatever C provides us. So this is the conceptual problem. This is why whenever we try to make an asynchronous program that takes the asynchrony and runs it between languages, we will always have to, it will never be smooth. It will never be exactly the experience we want to have, because the interface between the two languages just doesn't have the language which is rich enough to convey the concepts we want. And the final thing is that we could have had, it would have been great if that would be the only problem, but eventually FFI has its cost and asynchrony has its cost. Runtimes have their cost, and when you try to accumulate everything, you get performance which is less than what you would expect. So let's remember that, first of all, everything is allocated twice. If you have a JavaScript promise and it waits for a for a Rust task, then you need to have both a promise and a task. And whatever mechanism the JavaScript event loop uses to track that promise is matched by whatever mechanism the Rust runtime uses to track that promise. All the arguments that we pass, all the return values that we return, they're all marshaled. And everything is managed. If the higher level language uses a garbage collector, then it needs to remember the arguments. It needs to remember the callbacks. It needs to hold everything and track everything. And all of these have costs. And here, in our experience, in my experience, things just aren't as fast as we expect them to be. We expect an FFI call to take a few nanoseconds, but once we add to the allocation and tracking of tasks and promises, etc., things just aren't fast enough. And here I'm getting to the solution that we found, which was to not use FFI for asynchronous computation. When we've, in my work, when we've experimented in single-threaded languages, JavaScript and Python, we found out that we can just send data over Unix domain sockets from Python back to Rust, from Rust back to Python, and it would be faster. But why is it faster? Why is adding more things faster? So what are Unix domain sockets? The first thing to know is that they're also available in Windows. So in case you're wondering about the Unix part, it's not an issue. But they're aimed at passing data between processes, different programs on the same machine. So you take data from one process, pass it to the operating system, and the operating system then passes the data back to another process. This doesn't solve our problem of marshalling, right? We still have to marshal the data, potentially even twice. We need to copy it from JavaScript to whatever format is used by the socket, and then from the socket format back to whatever format Rust uses. We actually might pay more because beforehand we said we need to speak in CABI in order to speak between runtimes. But now we need to talk in operating system speak. We need to talk about context switches. We need to talk about system calls and kernel calls. And these things are expensive. These things cost a lot. And yet, I'm giving you all these arguments, and yet, for us, they are faster. Why? So my explanation is very simple. A lot of people put a lot of effort into optimizing one-sided communication from Java, from Rust, from JavaScript to Unix domain sockets, from Unix domain sockets back to Java, to JavaScript, to Rust, etc. There's significantly less effort on the specific FFI interfaces, right? Less people work on specifically Java to Rust FFI, specifically JavaScript to Rust FFI, specifically Python to Rust FFI. And this matters because, as we said, the languages, each one of them has unique concepts and an optimization which works in JavaScript and doesn't necessarily work, at least that works when you call from JavaScript to Rust, won't work when you call from Python to Rust. So the fact that you have generalized optimizations and a lot more attention for Unix domain socket might mean that at the bottom line, they're just been optimized further than the specific FFIs. And the Unix domain socket is a generalized interface. It's a stable interface. It's been stable for years. and there's a lot of attention into it, and it's an efficient interface. So I can see practically why it might be faster. But why conceptually is it a replacement? So we've had this slide, right? The Java executor talks to the to the Rust runtime using C, and I've complained that there is no ABI, there is no language for async operations. But that wasn't true, because there is an ABI for async operations. I called it here, I gave it an example, Unix domain sockets, but there is an ABI, and it's called the operating system. What do I mean? We said that runtimes schedule CPU time between concurrent tasks, right? There's something to allow multiple tasks to run concurrently at the same time, and the runtimes balance resources between them. And what does an operating system do? Exactly the same thing. It schedules CPU time between concurrent threads, between concurrent processes. And again, an operating system receives significantly more attention and more optimization and more effort than any specific runtime. So if I'm using the operating system as the ABI, as the interface between runtimes, I could get better performance because it's just a better interface. Now, this is specifically our experience, and I can tell you that I specifically said this is our experience when we've benchmarked in JavaScript and Python to Rust. Those are single-threaded languages, at least for now. We've had significantly different results when we've tried using Unix domain sockets in C#, a multi-threaded language, and Rust. So there's a very big, your mileage may vary here, but I wanted to communicate the fact that FFI is simply not the only game in town if you want to talk between languages. And there is another system, the operating system, which gives you a very similar concept to async FFI and might be even more efficient. So I have some final thoughts, and then Rainer, if we have time, I have some side points to make. Let's go. So first of all, there's a difference between async framework, right? Runtimes, executors, event loops, they don't only have different names. There's different concepts happening, and concepts, they're built differently, and they don't speak the same language. The core problem we have is that we're trying to convey a simplified async interface, right? Which is, as I mentioned, it's easier in the last 10 years because it is a simplified model of what was once concept. But each language simplifies it differently. And also each Rust runtime simplifies it differently. And this semantic difference is hard to bridge. And it's hard to bridge partly because there is no language that has the vocabulary needed in order to convey these concepts. But we do have something that can convey these concepts, and we do have something with the vocabulary for async computation, and that's the operating system that you can view as a meta runtime. And if I've convinced you that running async futures is complex across languages, well then, async streams with multiple return values, that's a whole nother ballgame. Rainer, do we have time for some small tips and concepts? I can't hear you. I don't know if others can.
I'm very sorry, that was my mistake. My mic was still muted. I'm sorry for that. Shahar, super interesting talk. We already have some questions in the audience, and I have some questions too. But don't worry, take a few more extra minutes if you have extra things to tell us. We are very much interested in.
Okay, great. So I hand-wavingly said that different runtimes have different behaviors and different concepts. And I just wanted to give you one example and one solution to how to bridge that. Rust async futures are lazy. They have the concept of polling. As long as you poll them, they advance. When you stop polling them, they don't advance. If you drop them, they just stop working. They're cancelable. Most other languages have different kind of promises. They have eager promises. Once you start them, once you start executing them, they run. They're uncancelable by themselves. The code in them can just return and stop working, but there's no interface to stopping them. This means that if you try to bind roughly a future to a promise, you might accidentally cancel that future or forget to poll that future and thus leave the promise hanging. But there's a simple solution to that, and it's called task spawn. Task spawn takes a future, a Rust future, passes it to the runtime and says, again, in a very simplified manner, run this, inform me when you're done running this, but if I'm not following it, if I drop the handle following it, continue running it. And that makes a Rust future behave roughly like a higher level promise. Another small lie that I said before, in my example, I said that whenever we call between languages, we have to marshal a callback, right? You've completed the computation and you need to call that callback. And on every call, you have to marshal a callback. And that could be expensive. And there's a simpler solution. You can make some kind of static callback or a callback per object, but a callback which is marshaled once. And keep that callback alive. Keep a list of waiting futures on the Java side with the Java callbacks, with the callbacks that you need to call back in order to continue the Java computation. And then when you call into the Rust side, you don't need to marshal a callback. You just need to marshal an index into that list. The Rust side, with the callback that was marshaled once, can call that callback with the index. You use the index in order to get the actual Java callback for this specific computation on the Java side and execute it. And essentially, this is an example with callbacks, but the same is true for everything. If you're passing the same string over and over again, don't marshal it again and again. Marshal it once. Keep some kind of pointer index, something like this, to it, and use that index, use that pointer. Pass that primitive. And we said that primitives don't need marshaling. They're the ABI that C provides us. And that will reduce the cost. And that's all. You can occasionally find me on no longer Twitter. And now's the time for questions.
Perfect. Thank you. Thank you very much. I just saw that Stefan is already in the broadcasting studio, so I will also get him on the stage now. Hi, Stefan.
Hi, everybody. I hope you can hear me all right.
Yes, we can hear you
Fantastic.
very, very good, very good. Okay, hey, thank you, Shachar. It was super, super interesting. I have some questions on my own, but of course, the questions from the audience have priority. Let's start with the first one, and I will try to display the questions here on the screen. And one question was, can new mechanisms like parking lot or I/O ring help? I think that is generally in this topic. Can you tell us something about this? Are you familiar with these concepts?
Um, so these concepts are essentially, I'm being very simplistic here, but they're operating system primitives that allow for more efficient async computation. Things like the ability to mutex cheaply or to queue a lot of operations on the operating system and let the operating system call you when one of them or some of them complete. And they certainly help us make efficient async operations on either side of on the side that interacts with the operating system, right? So if you're sending on a network, I hope that whatever you're using, whether it is Rust or any other language, uses the most efficient operating system primitive. Whether they can be used in order to communicate between the languages more efficiently, maybe. I need to think about how. It's a bit hard to say out of the box, yes, specifically use that way and it will work best. But yes, maybe. It's just a question of whether you, but if you do that, it means that your FFI framework only works on the operating system that supports IO ring or parking lot or whatever.
Got it. Got it. Thank you. Thank you very much for the statement. The next one is a very interesting one, and I will show it here on the screen. And I would like to ask another question on top of this one. I think it says without using built-in language runtime, like implement runtime explicitly for FFI without using Tokyo or Java runtime. And when I read that, one word comes into my mind: WebAssembly. Will WebAssembly solve all these problems? Will we have will WebAssembly get rid of FFI and have a common implementation of threads or whatever and garbage collecting? Will it solve everything? That's my question on top of this one.
I was a bit of a WebAssembly expert, but that was 3 years ago, and from what I understand, that standard is moving fast and advancing. So as far as I know, WebAssembly can't really do that, not simply because it's a closed box, right? WebAssembly does not know about network, for example. It needs to call into JavaScript, into the browser in order to communicate with the network because it's a closed box in order to be safe. So I don't think this is something that WebAssembly can simply solve, but I might be wrong here. In a more general sense, it's a very big question and a bit vague. I'd say that at least on the Java side, you cannot perform Java, JavaScript, etc. You cannot perform async computations without the built-in language runtime. Rust has this, I think, unique ability to have interchangeable runtimes. I actually just today read an interesting article saying that this is a bit of a myth, and it's in. I'm sorry, I don't have the link. I didn't integrate it in my notes, but it's in the latest This Week in Rust about how it's a bit of a myth that our runtimes are interchangeable, and essentially Tokyo is the one true runtime. But I think that if you're willing to write a Rust extension to Java performing specifically to Java, you might be able to do that. But again, you'll need to do something which is specifically for Java, specifically for JavaScript. And you'd need to hand tailor everything. And even then you'd have to use whatever the Java executor gives you. And since these executors are meant to work in Java, the interfaces they provide you for other languages aren't very good. I think the exception might be Node with the Node API, which allows you to create promises in C and C++ code. But most executors just don't have a native side interface that is simple to integrate with. They only think in Java or in C#. They're solipsistic. They're not aware of a world outside of themselves.
Super interesting thoughts. Thank you so much, Shachar, for these interesting slides, interesting talks, interesting ideas. What do you think, Stefan? It was an amazing talk, wasn't it?
It was very interesting, yes. So I had to scratch my head a couple of times because I never had this problem. And I was thinking while you were proposing your ideas and how you approached it, I was thinking, how would I have solved it? But I would never have gotten to the idea of Unix sockets. That's pretty neat.
Very interesting, very interesting. Shachar, we very much hope that you enjoyed your virtual hour here in Linz. If you ever come to Europe, you are always welcome as an in-person speaker, but you are also always welcome on this channel for maybe doing another talk if you have other ideas where you say, hey, this could be something that I would like to present to the Rust community. Please get in touch with us. It was a pleasure having you this evening here with us in Linz.
Same here. Thank you very much.
Thank you very much. Greetings to Jerusalem. Bye.
Bye-bye.
Bye.
Bye.
And with this, right. Stefan, hi, how are you?
Hi. Excited. So I'm always a little bit nervous before giving talks, and this one is one very dear to my heart, so I'm even more nervous and excited.
I mean, if you are a little bit nervous, these talks are always the best ones. I'm really very much looking forward. I'm very much looking forward to your talk. I think I do not need to introduce you, Stefan. We founded the Rust Linz community together. Stefan is a super well-known coder in TypeScript, in the web world, in Rust, and in many other technologies. And yeah, thank you, Stefan, for taking the time to present.
You're way too kind. Thank you very much.
Now we are back from Jerusalem in Leonding. Stefan and I, we are both in Leonding, and now I would like to hand over the stage to you. Stefan, I will bring your screen here on the stage. And yeah, I'm looking forward to your talk.
Okay, a little bit of window management here. All right. So hi, everybody. Welcome to my talk, Trials, Traits, and Tribulations. Here we are. Okay. Hi, I'm Stefan. This is my Mastodon handle. I also am on X Twitter. And this talk, I have given it originally at Eurorust last year, and I was eager to present it again because I really love the story that we did here, because it's a story about the time when we at Dynatrace, the company I work for, when we adopted Rust. And yay, we adopted Rust. So that's the first thing. That's fantastic. And this is what we did actually. So it's one of those things that, we wouldn't have been able to do without Rust. We created our own JavaScript runtime. Pretty amazing, huh? So it builds up on V8, thanks to the Nano team for providing fantastic Rust V8 bindings. We make very much use of that. And the idea is that you have two modes of executing JavaScript. One mode is the application mode. You have an application on disk, you load those files, and then you execute them in a worker. And the other one is having ad hoc codes that come in from an event source. So you say, oh, user X wants to execute this particular piece of JavaScript right on the worker, and it comes from somewhere, and we don't know what it is, etc., etc. So there are two modes. They are slightly different. And this was our first idea when we adopted Rust. And this project was pretty popular within the company, and we got contributors from other teams as well who wanted to try out this new language. And then, we got contributions like this, for example. Somebody was trying to load some files from the disk. They wrote a function called get directories recursively with root of type pathpath. They weren't sure if they really wanted to do that, so they did, of course, a code comment. They said, okay, this function gets directories recursively from a root directory. And actually, while they were developing, they found out, well, actually, they are using a non-recursive approach. With the comment, the function name might be misleading. So close. But anyhow, this is very honest, actually. The example that I just showed you shows that code is evolving. Often we start out with a totally different idea that we end up with, and further down the road, change will be inevitable. So especially if you're new to a new programming language like Rust, a programming language that doesn't allow you to cut corners, and is therefore often seen as hard, you will most likely spend more time fighting the borrow checker or working with wrapper types than thinking about good software design. And this is the content of my talk today. I want to go with you through a piece of code that ended up very varying, very hard to maintain, and give us real headaches, and which we refactored over the course of time into something that allows us to write features faster, that is easier to read, easier for our colleagues from us to be onboarded, and easier to contribute. Big disclaimer up front, everything that I show you is fictional, but rooted in reality. So I took a couple of code examples, I massaged them into something that hides all the details that I'm not allowed to talk about. But what you see here is something that, mimics the real world. So if you think about a couple of semantic decisions that, hey, they don't make quite sense to you, yeah, it's most likely lost in the translation of, removing all those details. And this is the culprit. This is the function at large. And you might say, come on, Stefan, what's your problem? This fits on a slide. Well, actually it doesn't. So there are a couple of lines down there, which I cut off. And at the lowest font setting, and I removed about 200 lines of monitoring code as well. But still, this function is called event handler. You're not going to see that. You're going to see that later. And it connects the event source to the worker, where we decide which strategy to use, if it's an ad hoc app, if it's an ad hoc function or an application function. And it has a couple of tasks that we are going to figure out together. The very first question that you might ask, and this is a very important question, is, do we need to change anything? If this code is never touched again, then just keep it like that because it works. Why bother? Let's just forget it, never look at it, use the VS Code collapse feature, put a nice little blanket on top of it, and ignore it for the rest of the time. But once we do need to change something there, things might get hard. And a couple of things show up. Like first, this is outright overwhelming. I wouldn't know where to start. I can't keep a mental map of this code in my head. I can't keep a mental map of my code in my head, let alone the code of an entire team. There's lots of indentation. It's very hard to navigate. We have unclear responsibilities. What does what? Why are things like that? It's very hard to see. And there are lots of similarities which, make it even harder to figure out what's going on. It's hard to keep in mind what's happening. And this is why we need to refactor that. So if you wouldn't have touched it, if you wouldn't need to maintain this piece of code, then just leave it like that. But otherwise, this is your work. The first thing that I always do, this is the first trick, I collapse. So I just go to the first indentation and I collapse everything so I get stuff on the screen and I can see what's actually going on. I try to understand what's happening on the first level. And there are a couple of things that we see. For example, we create a new configuration. Okay, that's good to know that we need some sort of configuration. Even though we don't need the details, we at least know that a config is needed. And then we see, once we handle the requests, we check for the application mode, okay, and then we go into this else if else construct, where we say, okay, the other mode should be ad hoc, but we're not checking for ad hoc. We are checking if a condition for ad hoc is met. And then we have a general else branch that, if everything goes wrong, stuff will most likely happen in there. So, okay, we get some overview. We know a little bit more about our code. So that's nice. Also, if we look at the function signature, we see that we are returning a result, a handler result. This is our return type. This is what we expect. but we are also able to return any error. This is a boxed error of a trade object that is thread safe. So we also know that if there is an error, we can just return it because we don't care which error it is. It can be any error. Good. Stuff that we found out by just collapsing our first level and get some overview of this monstrous 1,000 line of code function. Next, we open up the first if statement or the first if branch. And in there, we see another if branch. Apparently, we check if we get an URL from the event source, which listens to the name health, very funny name, then we do some extra checks. So in our application, we load those files from the application mode and see if they can be parsed. So we have an evaluation going on. It says it even here in worker evaluate, where we evaluate the code if it compiles, if it can be run. Otherwise, we wouldn't run it. Otherwise, we say, okay, let's return some error. And there are a couple of very interesting things in there. First of all, one thing that I didn't understand was that we check if the evaluation causes an error, then we unwrap it, and then we wrap it again, and then we return it. So we get an error, we unwrap it, we wrap it again, and there's a simple solution for that, which is error propagation. So instead of doing that, instead of looking into the error, just add the question mark operator. If there's an error, just bubble it up. Otherwise, continue with the result that you get. This is what I like to call happy path programming, because you just take care about the stuff when everything goes right, when everything is okay. And if stuff breaks, just bubble it up. Fantastic. The next one that you see is that sometimes we just return a okay message. This happens at several points, but also here at the health check. This is the first occurrence that we see. And this has been highly debated at Eurorust, but we, in the domain that we worked in, we can think of that as a default response, like something that we want to return in case there is no deviation from the default, from what we expect. And if we think about it as a default response, we can implement the default trait. So the first trait that we implement for our handler result is, well, default, where we do just the same thing. And we replace those 3 lines of code with the new line where we say, okay, let's create a default handler result. And you know, it's just 3 lines, but this is not about avoiding redundancy or about abstracting something away. You could use a function or just set defaults for the optional fields or whatever. This here is to communicate intent. The default trait says that this was meant as a default. I know what I consider as default. My team members know what we consider as default. And even Rust can instantiate the default response if a handler result needs to come up somewhere in a different struct. And this is what abstraction is actually all about. It's not only to reduce code and avoid redundancy, but also to provide semantics and context. We hide the unnecessary parts and provide the important parts. A status code of OK as U16, that's an implementation detail. That this is a default response, that's something that we as a team can do much, much more with. Alrighty, not done with the function, there's still this part where we load code from a path and then get the file name. And the file name is interesting because V8 needs a file name to work with. Even if they don't mean anything, you can write anything in there. But for every execution or evaluation, you need to provide some file name. And there are several types involved. We start with a path path. Then the file name function gives us an OS string, which we map to a string. And you know, this can error. This is an operation that can fail. So we call unwrap, and then we call toString to get an onStruct. The first thing that comes into mind is the unwrap function. You know, it should be safe. Haha, famous last word, but hey, at least provide a fallback, you know, something like no file name found. And we could leave it like that. It's a bit safer than before. But actually, this piece of code comes up again and again and again in our code base. In the health check, in the actual execution, even in the ad hoc mode, where we set it to just any random string. So this is also a process where we have certain semantics in mind. And by repeating it over and over again, we risk that we differentiate between implementations at some point. Or we just forget some very important detail. And what I like to do here is I'd like to introduce my own abstraction, my own type. a new struct that is a wrapper type for file names. I like to use tuple structs here with one field, because what we do here is we take a primitive data type that already exists and lay our own semantics over it. We separate the knowledge of what it is, not only in the variable name, but also in the type. To get from a path path to a file name, we use a conversion trait called from. Again, this is the same code as before, and we could easily just use a parsing function somewhere. But again, this is about communicating intent. And this reads like English, from path path to file name. Fantastic. It tells us a story. It tells us what to expect. And back from file name to string. Simple conversions that tells us what it is and what it's compatible with. We can focus on the task of converting without needing to look at the actual conversion. And then we create another default for the ad hoc case, where we say, well, it's just script.js. Whoever, I don't need to have an actual file name. It's just the code. So for the ad hoc case, we use this. All right. And with that, we can reduce this part to, just a couple of lines. Our health check now is super small, 5 lines where every line tells us exactly what happens. And if we take the file name type in the rest of our code as well, we can even save 1 or 2 conversions for later. And, also those changes have some effect on some code in other parts, because we can reuse the handler result default, we can reuse the file name. This is code that is getting repeated throughout our program. So what did we do? First, we introduced defaults. We made good use of error boundaries, fantastic, and we introduced our own type. But there's more. We learned about the event handlers interface. We got some information on which types are necessary, what the domain is about. We work with files and codes. We return something that looks like an HTTP response. And more importantly, we understand now that stuff can get wrong, and then it's okay that we return errors. Okay, to the next example. This is something that comes in the configuration section a lot. We look at a headers hash map and check if there's some particular key in there. And if it's there, we get it, we map it to something that we can own, and then we unwrap it. Some of those keys are optional, and other keys are required. And there's also a lot of domain knowledge necessary to understand what's going on there. And I especially like that we check if something is there, and then we get it and unwrap it. I don't think this is how you're supposed to use the result type. And this operation comes up a couple of times, 5 or 6 times in our code. So why don't we introduce another type that abstracts this? Since this operation can result, the first thing that I do is create my own error, because it's a header error that could happen. To create a header error, I just create an empty struct. I'm not cared about any contents. I'm just care about the error itself and the need to implement the error trait, the debug trait, and the display trait. Now I have an error that I can use with a boxed error, with whatever. And then I create another struct, a header struct that wraps the hash map. And then I implement two methods, one to get a required header and one to get an optional header. And I think this is beautiful, because the method signature tells us everything we need to know. Required headers can cause errors if not present, and optional headers, well, they can be absent. That's what an option tells us. And just as with file name, we added our own semantics on top of a standard data type. The characteristics of the data structure move to the back, and our goals of what we want to achieve, that comes forward. Again, abstraction is here to hide the unnecessary parts and provide information on the necessary parts. But I think headers is a little different. Where file name is a type that serves as intermediate carrier between a source and its ultimate destination, we invented headers just to add some more methods, to make extracting a header information more convenient. And we should wish our original data structure actually would have something like this. Something like this feature, or characteristic, or dare I say, trait. And this is what I do now. Instead of a struct header, I introduce a trait header. It tells us, again, everything that we need to know. It tells us everything that we care about. And instead of implementing the header struct, I implement headers for the hash map of string and string. It implements the right methods, it implements the right results, and we know about the right errors. If we ever decide to change the underlying implementation, our event handler code doesn't change at all. It's just a concern for some other part of our program where we decided that we want to have a hash map and not for the way we get our information. Why should we care that our headers are a hash map after all? We're just here to talk about those headers. And this is how we use it. I get the required headers, optional headers. The question mark tells me that there can be an error, so I bubble it up, and I know from the method signature what's going on, and I reduce my code effectively. Okay, a couple of little changes in the config part and in the app mode part, but now for the main act, and this is going to be something. Breathe, 1, 2, here it is. This is the application mode part, and again, I hope you can see it. If not, let's wait a little bit. We make it better. It must be very readable for you, but the contents are actually not that relevant. What we see is that we can apply some of our learnings already. First of all, here I have again a file name that I create somewhere. So I have a struct for that, bam, reduce it, and just call function path.into, done. Here on the next line, I check if something is some, if the option is there, and then I create some, otherwise I create none. So this is like doing the same thing, which is actually here. There's an option API to convert one option into another option. This is what I'm using here, so it gets smaller again. And now that I reduce those lines, something new comes into the view. A default handler result. Look at that. It's the same handler result that we had before. And you know what to do there? Call handler result.default, and it gets smaller again. And now we are at this point, which is very interesting. I have two method calls. One here is to map the execution of my worker to a result. And the other one is something where I just return an error, error.into. If it's an error, just return it. And since we already introduced proper error handling with error propagation, we can get rid of all the mapping functions and use error propagation. And now look at that. Now everything from the worker part with the application mode fits on a slide. It's still a lot, but it fits on a slide. And now I take this part on the left side and put the ad hoc mode on the right side. And they look a little bit different, but we can already see some very similar structures. App mode has a clear distinction between a runtime error and the result. In ad hoc, I can have both errors and results, which is weird at first, but then again, I'm having a JavaScript runtime. Hey, so this can happen. But that's it for reduction right now. Let's look into other similarities. In all cases, we need some code. We need to get the code that we want to execute. We need to get a file name, a file name so the V8 runtime knows what to do. We have some payload that we have, some payload to invoke our function with, so you can work with. And in the end, we execute it and, create the result for that. So those are the similarities that we have here. We need to get to those parts from somewhere. And we have the same preconditions, even the same properties, but how they are executed, they differ slightly. And this is something that reminds me of something that I learned 20 years ago at university, which is the strategy pattern. And I don't know if you heard about this traditional design pattern. I forgot it, by the way, so I was so annoyed by everything Java and enterprise that I annoyed all the learnings that we had 20 years ago. But then I found out, in that regard, actually it makes kind of sense again. What I have here is I have an executor that doesn't know about the actual implementation of the strategy, but can plug in one of two different strategies to work with. Either it's the ad hoc strategy or the application strategy, and it just takes the right properties over an interface that is, there for both implementations. This is the trait for the strategy. Where we can find the same for things that we saw in the execution of the app and the ad hoc mode. We find the file name, we find the code, the payload, and parsing a result. And look at those method signatures. It's so clear what to expect. File names gives a file name, a struct file name. Code gives us probably a string, or it errors if the error, the code is not there, or for whatever reason. Payload is a 30 value. And both health check and parse result can give us a handler result, so we can return from it, or we're getting an error. It becomes very obvious what every part is about. Those are the things that we need to provide for our strategy. All right. And then we implement the strategy for ad hoc. So first, I create a new ad hoc strategy. I say what the task is, don't worry, that contains just some information. And I want to come from the event that's coming in to the strategy through a conversion function. Again, it tells me, I want to come from that to that. Now I have a strategy, now I can work with it. And then I implement the event strategy for ad hoc. And look at that, it's not important what every line does, but you see, once we removed, or once we found out all the parts that we actually care about, every line that we implement becomes almost just a single line of code. And maybe, the handler result that we do down there, it's just setting properties based on what we get from the worker result. So it becomes clear what it does. And every method here tells a story, is easy to maintain, and we know what's happening. And we see our old file name type again. Look at that, how beautiful. Then we execute it. This is the executor. It takes one strategy. I've chosen to use a trait object just because it was the closest thing to do. And then we have all the 3 steps from the original function. So first of all, we are getting the file name. Then we are getting the code. Then we are getting the payload. We feed our worker with it. And then once we have executed it, we parse the result and return a handler result. This is the execution function. And this goes for every strategy. So I could show you the implementation for the application strategy as well. It's a little bit bigger, but those are the same implementations. And this is everything that we need. Again, we focus on the process, maybe very much like the original code started out to be, but then we put away the details to some other place. Okay, so what's this? Do you recognize it? This is how our event handler function looks now. First of all, we have some reduced configuration. It's not 100 lines of code anymore. Not at all. It tells us exactly what we are getting. And then we think about a strategy. We think about a strategy, and based on the enum, we are creating a new strategy. Either it's an app strategy or it's an ad hoc strategy. It's suddenly we are not in this weird if else construct anymore. Not at all. We now have a strategy that we can work with. And last but not least, we execute with our strategy the process from the executor. We pass it here as a parameter with the config and with the worker. Then again, based on the path, either itself, we call the evaluate call and return early without executing anything, or we execute it and actually execute JavaScript. So it becomes much clearer what's happening here right now. And we have 3 very distinct blocks that are separate from each other, where you can find in every line of code what's going on. Beautiful. So this is actually one thing that we can now maintain and work with and extend to our needs. So we have to ask ourselves the question, hey, was it worth it? So first of all, we got rid of all potential panics. We have proper error propagation. We know when we propagate an error, and we know which error we propagate. Fantastic. Also, we can change things where they belong. We have now much faster iterations because we are just taking one particular method and change something there, or add a new method if we want to introduce a new feature. So we don't need to parse this humongous function again to see where we need to change all the details to make all those modes work. We can do it within those modes very clearly. And I don't know if you can hear my split screen, but I can. And we can test our features in isolation. We can even have a mock strategy so that we know what's going on there. If you just want to test the executor flow, or we can test the strategies in isolation. And contributions are easier as our code communicates clearly what's going on. Still, there's a lot to do, in my opinion. Is it better? I don't know. Is it the best solution? No, sorry. Is it better? Definitely. Is it the best solution? I don't know. My colleagues came up with something entirely different, but equally helpful. So it's again, a good solution if you just try to refactor it. But we have a lot of things to do. We can maybe select a strategy earlier. We need to ask ourselves if we need to work with trait objects. Do they have a downside for our case, or are they okay for our case? This is something that we need to figure out. What about all the reference counters that are introduced? Can we have clearer structs that maybe work with references? Why do we need to share them? And are we okay actually with cloning a few elements just to, comply with ownership, or should we do something better there? I don't know. But this is something that we can now figure out much, much better, since we can look at our code and see what's going on. If you have 3 learnings from that talk, first of all, use proper error handling. Write for the happy path. Use error propagation. It makes your code so much more readable. Introduce your own errors if you want to have some errors. And interfaces that return a result speak a lot to you. They tell you a story. They tell you what's going on there. I implemented default and conversion traits, but in general, implement traits from the standard library to communicate intent, communicate what's going on. Especially going from a path to a file name. There's a process behind it, but you don't need to care about the process. The only thing that you want to care about is that you go from a path to a file name. And this is something that we communicate by implementing standard library traits. And if you want to abstract for semantics on types that already exist, use your custom traits and types. We introduced the header type, which is beautiful because we can remove the underlying implementation for something entirely different, but everything stays still the same. We introduced the file name type, which, tells a different story than just a string. What's clearer, a string called name file name, or actually the type file name? And you can have multiple file names with different names. We introduced the event strategy trait, which also tells a lot about what to expect. And we can hide all those implementation details. And those are the 3 steps for refactoring that make your code base a little bit better. And I want to thank you a lot for your attention.
Stefan, thank you very much. I hope you still can hear me. I
can hear you. Yes.
Very good, very good.
But,
and I hope you can also see me. I'm sitting outside. I have a light here, and now I connected it to my laptop, and it died. So I hope it's still.
No, okay. I can see you. I can see you much better than I can.
Very good.
But yeah.
Very good. Hey, thank you for this amazing talk, for taking us on this journey about how to do refactoring and how to write really good really good code. We have one question here that came up during the talk. Let me quickly show it to you. Maybe there is one exception for question mark. You need to add serializable stack trace for your nested this errors, and to initialize one of the struct fields, you must use file exclamation mark, line exclamation mark, and column exclamation mark. Do you want to get into that one?
Yeah, okay. So I think what you're getting at is, so when I introduced my error, I just didn't care about anything. I just introduced an empty struct and slapped a couple of traits on top of it. And it was like, hey, yeah, go for it, whoever, whatever, it will work. But maybe you want to have more information there. And there's one thing that is important here, is that you can not only introduce your struct, your header structs. I'm so sorry, my kids have, I don't know if they are fighting or if they have a lot of fun out there, but it's incredibly loud right now.
Okay, we can't hear it. Noise cancellation works great.
But what I usually do in things like that, I just had this boxed error. Actually, I can just bubble up any error and I didn't care about. What I usually do is that I have a very specific error when I have one part like the event handler, which I call, I don't know, handler error or whatever. And if I introduce my own error, I create conversion traits to that error. And there you can add some extra information without needing to bubble it up. And especially with the question from Cook-Moore that they had, is where you want to have a stack trace of where the stuff happened. If you abstract those things away, yeah, you're right. You might be able to lose the exact line and column where it is because it happens somewhere else. This is true. But I think if you're doing a right conversion, you are keeping at least the stack trace from where it happened. But I couldn't tell you that. I would have to need to look it up. I'm not using this error, so this is not the this error crate. You could use this error because it's basically a crate that does all that I do manually much, much better, and maybe has already taken care about the file line and column thing. Maybe.
Okay, thank you very much. Thank you. We don't have another question, but we have a huge compliment for you.
Oh,
I really like all
this
the
is nice.
insights for effective refactoring. Fantastic talk. Thank you. Compliment from
Thank you very
Daniel.
much.
Yeah, I can only second that. It was super interesting. Yeah. And thank you for taking the time to jump in here on short notice. I already mentioned it
Sure.
at the beginning that we had another speaker who unfortunately couldn't come because of scheduling problems, and you agreed to do a last minute talk. And yeah, I think you should always do last minute talks where you are a little bit nervous because they are really, really good. They are really great.
Thank you.
I'm not saying that the others are not good, but I really like this one. Yeah, thank you much.
Thank you very much. You're so kind. Alrighty.
Stefan, I think with that we are through. Let's just say thank you to everybody who watched today's Rust Linz meetup. It was a pleasure having you as our guests here in Linz, virtually here in Linz. And yeah, we are looking forward to doing the next Rust Linz meetup in October. We will see whether we make it a hybrid event or whether we make it a virtual event. It depends a little bit on on the traveling that we have to do, whether we have speakers who are locals who come to us. It depends. We'll see how it goes. Yeah, with that, I think we can close. Stefan, thank you very much. Thank you, Shachar, if you still hear us, and enjoy the rest of the evening. Have a beautiful few weeks until the next Rust Linz meetup.
Bye-bye.
Bye.